Hello, and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy. In this video, we define subgames and subgame-perfect Nash equilibrium. Then, we introduce backwards induction, our standard algorithm for finding subgame-perfect Nash equilibrium. Last time, we saw that a mistake off the path of play disqualified a Nash equilibrium in some sense. We introduced subgames so that we will have a language to make this disqualification precise. As with several of our previous definitions, the definition of a subgame is formal, but its meaning will hopefully be fairly intuitive. The game tree contains within itself smaller trees that represent smaller games. These smaller trees are called subgames. Here is our now old friend, dynamic battle of the sexes. First, let's find its two non-trivial subgames. Here in blue is what we will call subgame italic. It begins at the woman's node in blue, following the man's selection of boxing. It consists of the blue node with a woman's name on it, the two branches descending from that node, and the terminal nodes at the end of each of those branches. And here in blue is what we will call subgame bold. It begins at the woman's node in blue following the man's selection of ballet. It consists of the blue node with the woman's name on it, the two branches descending from that node, and the terminal nodes at the end of each of those branches. In addition to these two non-trivial subgames, note that the game is a subgame of itself, albeit a trivial one. This section introduces subgame-perfect Nash equilibrium. Subgame-perfect Nash equilibria are those in which strategies are credible, even off the path of play. A subgame-perfect Nash equilibrium is a strategy profile that forms a Nash equilibrium in every subgame. We say subgame perfection is a refinement of Nash equilibrium, because a subgame-perfect Nash equilibrium is a Nash equilibrium with some additional requirements. To say that play is everywhere credible is to say that we are everywhere in Nash equilibrium. Subgame perfection is the refinement of Nash equilibrium that captures everywhere credible play. Here is Selton's chain store paradox again, next to its matrix form with best responses underlined. In the previous video, we rejected the Nash equilibrium stay out, fight, since fighting off the path of play was not a credible threat. Here is enter, coexist, marked in blue. We know from the previous video that these strategies form a Nash equilibrium. The strategies also form a Nash equilibrium in the subgame beginning at the incumbent's node, because the incumbent prefers coexist to fight. Since these strategies form a Nash equilibrium in every subgame, they form a subgame-perfect Nash equilibrium. On the other hand, here is stay out, fight, marked in blue. Again, we know from the previous video that these strategies form a Nash equilibrium. However, they do not form a subgame-perfect Nash equilibrium, because fight is not a Nash equilibrium in the incumbent's subgame. Our rejection of this Nash equilibrium because the incumbent's threat to fight is not credible amounts to rejection because the equilibrium is not subgame perfect. We end this video by introducing backwards induction. As we saw in our study of static games of complete information, using the definition of equilibrium to identify equilibria is cumbersome, particularly in large games. We therefore want at least one faster method of finding equilibrium. In dynamic games of complete information, we use backwards induction to identify subgame-perfect Nash equilibrium. Here is the backwards induction algorithm. This algorithm is fairly old, dating I believe to 1918, although I can't find my source for that date. We start by identifying rational play from the end of the game. Then we work our way towards the top of the tree, identifying rational play as we go. When we reach the top of the tree, backwards induction ends, and the remaining strategies form a subgame-perfect Nash equilibrium. Furthermore, backwards induction will capture all subgame-perfect Nash equilibria. We'll practice using backwards induction on Selton's chain store paradox. The incumbent's move is the last. The incumbent prefers coexist to fight because 2 is greater than 1. Therefore, we remove fight and its terminal node from the tree. After removing fight, this tree remains. Now, the entrance move is the last move, since the algorithm replaced the incumbent's move with coexist. The entrant prefers to enter because 2 is greater than 0. We remove stay out and its terminal node from the tree. The entrance move was the first move of the game, so we're done with backwards induction. Backwards induction lets us conclude enter coexist is the unique subgame perfect Nash equilibrium of this game. Thanks so much for watching this video about subgames, subgame perfect Nash equilibrium, and backwards induction. In the next video, we'll take a closer look at the distinctions between Nash equilibrium and subgame perfect Nash equilibrium.